Yeah, let's starting recording, and then today we will go over some of the arbitrary read and arbitrary write primitives, and then how we can utilize them to exploit the vulnerabilities in the program. And for the around the 7 weeks, what we have learned it was like the try to exploit the buffer overflow vulnerability to run some of the your code in the form of shellcode, or like the running some of the libc functions, or it could be running rob gadgets. Yeah, but basically what we were doing is like the we try to alter the return address using the buffer overflow vulnerability as the entry gate for the changing the return address. And then to overwrite the return address, we also use some of the techniques to leak some of the address out from the program to figure out like where the printf or other function addresses are. And finally, we can call the execve to run a shell. And so we learned that as like in the form of like exploitation of the buffer overflow vulnerability. But basically what we were doing is like we were trying to change the return address value. And then to do that, what we need as a minimally was like just changing the 4-byte value or 8-byte value in 64-bit machine for the return address itself. That's it. And then if we change that, we can change the control flow of the target program. And another important thing is like that if we can have the capability of the changing the return address, that could be arbitrary write or buffer overflow. But the problem is that we need to know where we want to change the address. So for example, where we returns to. So for example, we would like to return to not printf, but for the execve. Yeah. So we need to identify where it is. And then in doing that, we will use arbitrary read. So basically, arbitrary write is for changing the control flow by changing the value of the return address or something. And then arbitrary read is for reading some of the data, collect some of the knowledge from the binary, and then we know where we return to do something that we want to do. So let's start with the challenge AR2 first. So that we will visit the sequential read one later, because that's the most difficult one in these sequential read 1, arbitrary read 2, arbitrary write 1, and arbitrary write 2, these challenges. So we will start with the arbitrary read 2, and then move towards arbitrary write 1, arbitrary write 2, and then we will get back to sequential read 1. So let's start with the arbitrary read 2. And this challenge is about, so in the main function, it runs a set regid for us. So what we need to do is just running the system function. That's it. Yeah. And then it calls the input function. And in the input function, there's a buffer, and then it will perform arbitrary read. We will visit that later. And then it will print up some of the string and then get input. So we have a chance to like exploit the buffer overflow vulnerability here, because the buffer size is buff size, but the read size is the buffer twice of the buff size. So we can launch buffer overflow attack here. But the problem is that this machine is with the this machine is a VMCTF2, so it is with the ASRL. So addresses are changing, and then if we check the security of the AR2, then it says there's no stack canary, so we can freely overflow the buffer and then exploit the buffer overflow vulnerability, and it's not a PIE binary at all. So in that case, what you want to do is you want to search some of the functions that is available in the program, because these are fixed address, so that we can directly call that. But what we have is the put, printf, read, fget, these kind of addresses, and nothing more. So in this kind of case, in ASRL 3 challenge, what we did was, or like the ROB5 challenge, what we did was like we would like to run the printf or puts to print out the global offset table of these addresses. Then we can get the address of these functions in the library. And then by calculating the offset between that function to the location of the system, then we can call that. That was in like a ROB5. But in this challenge, we have a capability of the reading the data arbitrarily from this function. So input function calls a read function, and then in this read function, what it does is like it will ask, so it will read n bytes from address A, and then n and A, for both of them, we can specify that. And then it will ask how many bytes do you want to read. So we specify n first, and then that will goes to the read size as a unsigned long integer. And then what is the address that you want to read? Then we can put in that in a hexadecimal value, then it will get it. Then it will be a pointer, and then it will just print out to the send that out, which is a console, so that we can get output from the program from the pointer, the address that we specified, and then about the read size, the size that we specified. So it will just delete some of the values from specific address. Then what we can do is, so an exploit sketch will be, so we will run arbitrary read here at first. And then in doing arbitrary read, what we will do is like if we can read printf GOT, and then leak the address, and then calculate system function address in libc, and then something like this, yeah, at here. Yeah, so with this arbitrary read capability, we can leak the GOT of printf and then leak the address. We can calculate the offset in system offset of the system function in libc, and then execute the system sum of the string. So we can always find the sum of the at sign around the start of the binary program. That's why I'm using at here, and then use that address as an for the overflowing the buffer. So let's do that. And then before that, we need to interact with the program. Let's take a look at the syntax first. So it will print out 2 lines and then ask for n. So what we need is just an 8-byte leak. And then we need to put the address, maybe 601020. And then it will print out some of the data and then ask for our name. And then if we type it, then it will output like this. Then based on this output, we will write an exploit script. So first import everything from pawn, and then we will use process AR2, arbitrary read 2. And then what we will do is p.elf GOT, then we will get the GOT of printf. And then to check if it works well or not, so we can see that it get the GOT of the printf from the binary correctly, 601020. Yeah. And then what we will do is so we will synchronize the output. It will print out first line and then second line. So it asks that how many bytes do you want to read? And then we will say what we will read is 8 bytes from the printf GOT, because what we want to get is the address in the library, the function address of the printf in the library. Yeah. So we just put 8, and then it will ask about the addresses too. So there's one more line and asking about the address. And then we will put the address as so GOT of the printf, which is 601020. We will put that. And then if we do this, then it print out the 8 bytes from the 601020. So it will output the reading 8 byte from something first, and then 8 byte, and then please type something. So what we can do is this receive line will receive this line, and then we will read 8 more bytes and then another new line. So we will read 8 more bytes for the data leaked, and then so we will print out new line. So now the some of the weird data is not printed here, but we can print with the print represent of the data like this. Then we can see that it printed out some of the address. And if we want to change that as some of the readable address, then U64 will change the data into integer, and then that will be the data link. And then we can name it as libc printf, because we just leaked the GOT of the printf. And then if we print out libc address of the printf, then it says 7F63B6C17810. But the easiest way that you can check if this is like a correct randomized printf address or not, so just focus on the last 3 digits, 810, and then go to your GDB, break and main, and run it, and printf. And then if that says 810, then you're on track. So you got the address of the printf from GOT. Yeah. And then what you want to do is you want to get the address of the system. And to do that, you can get the location of the, what is that? Location of the library ELF file. And then you can get the libc as the ELF object at here. And then libc the symbols. You can find the printf hit here, printf offset, and then you can get the offset of the system like this. And then now we have a libc printf minus printf offset add system offset. Then we can get the libc system like this. And after having the libc system, and we need to overflow attack the launch the buffer overflow attack to the input function. Yeah, and to do that, disassemble input function again, and then this is the target read function, and our buffer comes from RSI, and that is coming from RAX, which is at the RBP minus 0x80. So now we know that the buffer is something like, so at RBP minus 0x80, and then save EBP, and then return address. So we will form a buffer as a multiplier by 0x80 plus save the EBP as a blah blah. Yeah, and then we will add maybe pop RDI and return. Set first argument of system, and then call system. Then we will call system at, basically like this. And then to get the address of at, what you can do is GDB AR2, and then break a main, run it, and then print out some of the string from 40000000, then at the 40000020, you will see that the string start with at and then end with 0. So if you use this address, then it will regard the data as a string at. Yeah. Then so copy that one. So we will use the first argument of the system as this address. Then now we need the address of a pop RDI and return. And then that could be grabbed by rob gadget. And then for pop RDI return, we have this address. Copy that. Then we will just put 0x4008333. Yeah. Then it will do pop RDI and return, set this, and then call system. And we will send the buffer and then interactive. And then before running the exploit script, we need to write the at.c. Then to make it to make us the notice about that the exploit script is running, I will just print out some of the string here, and then the execv vnsh. There we go. So if I just run app, then it will say exploit is running. So I will just run py, but it ran some of the at sign, but it does not run the our at, because if we just run at, it says command not found. The thing is like our path is not included in the current the environment variable. So what we can do is we can include the current directory as a path. So we can create the environment variable path as current directory bin user bin. Yeah. And then set environment variable as an argument. Then it will run the exploit and then run at, and finally get the group ID of the program. So basically the exploit was like the if we have a capability of the reading n bytes from arbitrary address A, then to use that to utilize this kind of the arbitrary read for useful for the exploiting the buffer overflow vulnerability. So what we need to know is the address of the system or execv or any kind of other functions. And using this arbitrary read capability, we can read the GOT of printf to leak the address, and then finally figure out the address of the system, then we can run the program. Any question on this example? I believe this challenge is easier than the ROP5, I think. Yeah. So I inserted this challenge because it will give a brief overview of like how we can use arbitrary read for the other exploitation. So maybe you can feel it like a little boring about like the exploiting the similar thing again. So this challenge is very similar to ASRL2, ASRL5, or ASRL3, or ROP5. Yeah. And if there's no question, then I will move on to the arbitrary write one. So this is another easy challenge, and let's check that what the code is doing. So in the main function, yeah, you can see that there's an input function, and then in the input function, the structure is very similar. It has a write function that performs arbitrary write. But the interesting thing is that it has a push at here, and then it has a read function at here. But the thing is that it reads for the buffer buff size -1. So there is no buffer overflow vulnerability at all. And then this example is just there for demonstrating that we only have arbitrary write without having the buffer overflow. We can actually launch the control flow hijacking attack. And then to do that, what we will gonna do is like we will transform this printf call. So it has a printf call right after the buffer overflow happens, no buffer overflow, right after the read function executes. And then before hitting this printf, you can perform the arbitrary write. So what we will gonna do is like we will change the GOT of the printf. Before calling the printf function, we will change that address points to the this function. Please execute me. Then the printf call will not going forward to the like calling the libc printf function. Instead of doing that, it will call this please execute me function. So we will do that. So the program basically asks about like we need to put the n bytes and then address A, and then we can write the 8 bytes to the sum of the address, and then it asks about like the provided that 8 bytes, maybe like this. Then it will ask about our name, and then something like that. Yeah. So let's try to write an exploit script. So what we will gonna do is like we will change the GOT of printf to the please execute me function. So even if the program tries to call the printf function, it will call please execute me, not the libc function. And then we will do that. And then let's start the exploit script. So we will exploit the arbitrary write one. And then what we want to know is a p.elf.got. So we will change the GOT of the printf. So the exploit sketch is that change the value of printf GOT printf as the value of the please execute me. And then make the program run. When it calls printf, it will execute. It will run please execute me instead. So we will do that. And then to see that, I will use a debugger. So let's change the name as AWX. And then add an executable function to the script, and then I can copy the binary to AWX. And then let's set the tmux environment for this. Then we have the GOT of the printf, and then we also need to get the target function address, which is p.elf symbols. Please execute me. And then let's check if we get the values correctly. Print ADDR target function. Maybe I can add hex on it. Let's run this. And then it seems like we get the address of the printf the GOT here and the address of the please execute me function here. So everything looks like correct. And then after that, we will get 2 lines, and then we will type how many bytes we want to write. So we will just we will write the 8 bytes, and then it will ask for the address, and then we will provide the address of the printf GOT, so hex printf GOT. And then it will ask send our input. So right now, so what I will do is the p.send line, no, not send line, send. And then we will just send the 8-byte data, p64 of the target function address. Then what we just did with the arbitrary write primitive is like we send the 8-byte data of the target function address, which is the address of the please execute me function. And then we will overwrite that into the GOT of the printf. And then we will see how the execution will flow. Yeah. And then we'll do p.interactive. Then it ran a shell, but we will see why it is happening. So to examine that, I will execute the tmux first. Maybe. Then in the script, what I will do is gdb.attach p. Then now we are in the debugger. So we can disassemble info function. So maybe I can break after this one. So after calling read function. Yeah. So I will set a breakpoint at here and continue. No. So it ran the program anyway. So maybe we can set the breakpoint somewhere else. So just run the debugger again, and then so from the backtrace means that how the current execution is ongoing. So it was there are like some the depths of calling up the apt-get getLine and then all the functions, but it's in the read integer function, which is called from the write function. So we are in the write function here, yeah. And then maybe because our read function will change some of the printf call here. So this printf call matters. So what I will do is I will set the breakpoint after the read function that we call here. So no, not that address, at here, and then continue. So now we stop right after the reading our 8 bytes input, and then I will just print out what kind of values are here. So 602028, which is the address of the printf GOT. So it previously contains the address of the libc function printf. But right now, we changed that value with the arbitrary write to this value. This value was the address of the execute me. Then, so in the write function, we do not have any kind of the execute shell or please execute me, that kind of function call. But just take a look at that. It will move the instructions, and then finally, it will meet the printf call. Yeah, and then I will follow this printf call by doing si. Yeah, then it will get into the printf plt. But what printf plt is doing is just dereferencing the, this is actually the, just dereferencing the GOT of the printf. And then now the printf GOT contains the address of the please execute me. So when the program makes a function called printf, it will not call the function printf. Instead, it will call please execute me as a printf. So it will run get EGID, and then set EGID, and then exec BE with the BNSH00. That's it. So we just seen that with the arbitrary write, we can change the address of the stored in the GOT to the something else. Then if the program makes the printf function call, then that will be replaced by this function call. So by running this, we can get the shell, and then we can also get the group ID because set RegID is done by the challenge itself. Any question for this challenge? I believe that this one is also the one of the EG challenge. And then let's move on to the arbitrary write 2. Yeah. This is a similar challenge, but the difference is that in arbitrary read, we have arbitrary read capability. And in arbitrary write, we have arbitrary write capability. And then in arbitrary read, we were using the arbitrary read as a precursor for the buffer overflow exploit. And in arbitrary write, we don't need the buffer overflow exploit, but we can use that as like the changing the return address or changing the GOT. And then what if we have both of arbitrary read and write capability, then what can we do? That's the main question in this challenge. And just having arbitrary read and write, and that actually allows us having the control flow hijacking. So even without the buffer overflow vulnerability at all. And then to demonstrate that, I prepared this challenge. And in this challenge, what the challenge asks for is like it will do set regi ID for you. So what you need to do is just run system or like just running binsh. That's it. And then in the input function that main calls, so it will call read function once and then write function. There's no buffer overflow at all. And then asking you to exploit this program. And then this read function and the write function is the same one that we have seen in the arbitrary read and arbitrary write challenge. So we can specify the size and the address. Then we can read any kind of data for the first time in this read function. So we can do arbitrary read for one time, and then we can also do arbitrary write for one time. Then how can you exploit this and then get a shell? So previously if we have arbitrary write, what we did is like just changing the address of the printf GOT to something else, then it will let us to call some other function. Yeah. So we will do the same thing, but which function address do you want to put here? So previously we put the please execute me function, which is existing in the code, but there's no code at here. So we don't have that kind of the running shell for us function here. And then what we need to do is like we need to replace this printf function into system. Yeah. And then to do that, what we will do is like we will perform arbitrary read to leak the address of the printf or puts in the GOT. And then we can calculate the address of the system. And then we can use that to change this printf into system function. And let's do that. So let's write an exploit script here. So import all the font tools, and then we will exploit arbitrary write 2. And then start with the 2 lines and then ask about the how many bytes. Yeah. Then from which address. So I will put the print line straight. So print out 2 line. And then the question was how many bytes. So we will just read 8 bytes from the program because we just want to leak the one of the GOT entry. And then it also asks for the address, and then we need to put the GOT of the puts. So to get the GOT of the puts, the p.elf, the GOT, and puts maybe puts GOT. Let's check if we got the correct address. So the puts GOT is at here, and then we will read the 8 bytes from the puts GOT. So p.sendLine hex puts GOT. And then the reason why I attach hex is like that this is just an integer value. So I will change this as an hexadecimal integer, as the input format is like the hexadecimal integer here. Yeah. So after putting the size and then address, then it will leak the value. Yeah. So what we will do is synchronize the output, and then p.interactive. Now, after printing all the thing, then the first 8 byte is some of the address, I believe. Yeah, that will be the address of the puts. Yeah, so we will read 8 bytes, and then libc puts byte value of the libc puts will be this one. And then we can change this to U64 libc puts byte libc puts, and then to check if that is correct or not. So we can print out libc puts as an hexadecimal number, then run it here. And then to check that, just focus on the last 3 digits, 6A0, and then run gdb break and main run print puts 6A0, which is the same. Yeah. 6A0, right? Yeah. So we got the address of the puts right now. Yeah. So we successfully get the address of the puts, and then it will print out the 2 more lines for the arbitrary write. So right now, we know the address of the puts, then let's calculate the address of the system then. So let's get the location of the libc here, and then libc is, oh, maybe I failed on copying this line. So I copied it, paste it, and then libc dot symbols puts. This is puts offset. And then system offset is libc symbols system. Then libc puts minus puts offset, add system offset, and we can get the libc system. So now we have the address of the system, and then we need to perform arbitrary write here. So it will ask for the number of bytes first, and then we will write just 8 bytes. And then it will ask for the address, and then we will change the GOT of printf. So printf GOT p.elf, the GOT printf. So we can get the GOT of the printf. And then for that data, it requires binary data. No. So for the address, it requires a hexadecimal format of the address. So we send the printf GOT as in a hexadecimal number as a text. And then after sending that, we need to send the Oh, it's out of sync. Yeah, maybe I can fix the sync. So let's get back to the sending 8 bytes, and then it asks for the address, and then we can send the address here. Yeah. And let's print hex printf GOT. So the GOT of printf is here, so it's all okay. And then we may send some of the bytes that we would like to print. So we would like to put, so that will be the address of the system. So U64 libc system. We can send the data to the program, then it will put the address of the system in there, then the printf call could be changed. Maybe I did it wrong, not the U64, P64, because it's changing the integer number as a binary data. Yeah. And then it has a segmentation fault. Let's follow the execution with the debugger. So let's copy the AW2 to AWX. And then I will change this to AWX, and then gdb.attach p like this. And the terminal context Emacs split W and then dash H. Yeah. Then I will run tmux, and then run exploit. Yeah. Then right now it's stopped at here, and then with disassemble info function, and then in the info function we can set the breakpoint at here. Yeah. So what I will do is like I will set the breakpoint right after the running the read function. Yeah. So it's right after the read running the read function, and then it prints out the address of the puts. And then let's check if that is correct. So in the debugger, I just print out the puts address. It is 7F0FB5115680, 7F0FB5115680. So the address that we leaked from the GOT of the puts. Yeah. So my bad. The address is 602018, right? Yeah. So from the GOT of the puts, we can get this address of the puts at here. Yeah. And then from the GOT of the printf. So the printf GOT is a 28 actually. So that we can get the address of the printf at here. Yeah. But in this write function, we will change this into something different one. So let's get into the this write function. So si to follow the call. Now we are in the write function, and then it will put some of the data, and then it will read integer. And the integer that we read is stored in RAX. So we just send an 8 bytes as the how many bytes you want to write as an 8 bytes, and then it will call the put function again, asking for the address. Yeah, and then what we supply this is 602028, which is the address of the GOT of the printf. And then it will run read integer again. Then RAX is like a 602028, which is the printf GOT. Yeah. And then it says, please provide a max 8-byte input. And then it will run the read function call from the file descriptor 0 means the standard input. And then it will read up to 8 bytes to our supplied address. And right now it's stopped at our script side because it didn't send anything. And then after we send something, yeah, the read stopped. So from the debugger, we notice that we need to send something. Yeah. Debugger was stopped because we didn't send anything. So right now, after sending the printf.got, then it didn't get the right data for the libc system. So maybe we can print out the maximum 8 byte or death string and then send the libc system, then peanut interactive. Then so we can set the breakpoint at the write function. So right after the second read integer, break at here and continue. So right now it is asking about the address. So the now address is a 602028. So if I print out 8 bytes, then it will be the address of the printf, right? So this is actually targeting the printf GOT. Yeah. And print out that we need a maximum 8 bytes output. Yeah. Then it will read the data. It's still not reading the data from it. Yeah. I don't know why, but I believe its I/O is interrupted, but now it seems working. So for example, if I change not attaching the GDB and then changing to the arbitrary write 2, No, it's not working at all. So if I just do this, then it's stopped at the line 646. Line 46 is just printing this. Yeah, but maybe we can change this, not the receive line, maybe receive. Yeah. So now it's a stop at the receive. Maybe we can cancel it. Yeah. So if we remove all these 3 lines, then right after sending the 8 bytes for the read, then it's stopped at here. Yeah. So after the sending the 8 bytes for the read, and they ask like, what is the address that we would like to write, and then send the address. Yeah. And then it should send some of the data that asking that how many bytes we would like to print out, but it seems not. Yeah. So I believe that there's a little error on this. I believe the exploiter was working with the GDB. So for example, now I don't have GDB tmux right now. So what I can do is like I can attach tmux and then continue. And now we get the segmentation faulted here because our RAIX value is something weird. That's why. Yeah. And let's check that what's in the six zero 2028, which is the address of the printf. So we failed on like writing some of the values in here. Yeah, and then if we disassemble the write function, so it failed after the read function. So it actually gets the so RBP minus 10 is coming from here. So it's actually the address that we put as so this address, the address that we put for the target address. So might be there's a mismatching of the input and output, but basically how the exploit works is something like you need to get the address of the puts first with using the arbitrary read. And then after leaking the address, you can get the address of the system. Then you can put the address of the system to the GOT of the printf. Yeah. And then because of the time limit, I will move to the sequential read 1 challenge. Yeah, for the next. Yeah. And then this challenge is quite a difficult one than like the ASRL5 or ROP5. And then basically the challenge itself is the same, similar to those challenges. And what this challenge requires is that it contains a main function, and then it will call the input function. And in the input function, it will do, so it will give a chance to have a sequential read capability from the current stack. So it asks that how many bytes to leak from the stack. And then if we type the bytes, then it will read from the buffer up to the specified bytes. So the challenge itself is very similar to the ASRR 3 or 5, and it could be similar to the ROP 5. But what you need to do is like you can have some of the sequential leak here, and then you need to exploit the buffer overflow vulnerability here. So because it gets twice of the buffer size, so you can exploit this one. But the problem is that right now you don't know the address. And there's another problem. So if you run the pawn check stack, Then now the binary program has enabled with the PIE, NX, and stack canary. So all three defense are enabled in this binary. And then right now you have a one sequential read vulnerability and also the another stack buffer overflow vulnerability. So the challenge asks you if you can bypass all three these defense mechanism by having the sequential read vulnerability, and then can you successfully exploit the buffer overflow vulnerability at the end? And then the answer is yes. And then I will demonstrate how you can do that. So because stack cookie, NX, PIE all protected, so breaking PIE is easy. So you need to know the code address, and then you will reuse that. And then maybe there's a sequential read vulnerability, so we can find some of the code reuse part at there. And then for the non-executable, yeah, PIE and non-executable, these are all ASRL and the DEP related things. So after you figure out where the function is, then you can break both the ASRL and DEP here. And then another thing is like a stack cookie. So to bypass the stack cookie, you need to know the value of the stack cookie itself. So let's do it step by step. So we will steal the value of the stack cookie first, and then break the ASRL and launching ROP. So we will break the stack cookie first, and then the launching ROP for the bypassing NX. But to do that, we will break the ASRL to bypass a PIE. Yeah, we will do all three things by exploiting the two vulnerabilities. One is a sequential read, and then the other is a buffer overflow vulnerability. So let's writing the exploit script here. So let's go to sequential read one, then I will write the exploit script. Then sequential read one, so we will exploit that. And then this sequential read one binary. So it prints out 2 lines and then ask about the how many bytes. And then if we type 200, then it will print out the 200 characters, and then that's it. So my terminal gets weird because it will print out some of the weird 200 bytes. And then to get it correctly, so you can do it something like this and then type 200, and then you will see that some part of these 200 values are something like this. And then some of you can identify some of the stack addresses here, 7FFF41DD or something. And then if we run it again, that value will be changed because the stack addresses are randomized again and again. Yeah. So it seems like that we can leak some of the address from the program. So let's write it. And then first we need to synchronize because we will utilize some of the program's output. So we need to synchronize the program's output. So to do that, so because it gives two strings, 2 lines of the strings, so I will get them get them and print out in the console. And then after that, I will just send 200 as we will just get 200 bytes. Leaking from the buffer to some of the addresses. But let's think about how the buffer structure is in this challenge. So we are overflowing this buffer, this function call, and then our buffer is at EBP minus 90, and then our stack cookie is at RBP minus 8. So let's draw some of the buffer here. So our buffer is here. And then the address of this one is RBP minus 90. And then stack cookie. And then this is at RBP minus 8. And then after 8 byte, we have RBP, save the RBP here. And then return address. And then something more. Yeah. So we can leak 200 bytes, maybe 300, 400, whatever we can put, but I just put 200 here, then it will leak the 200 bytes starting from here. And then right now I'm mixing the hexadecimal and decimal numbers, and then try to take a look at what is the size of the 0x90. 0x90 is a 144 bytes. So, which is definitely smaller than the 200. So 144 bytes of the buffer and stack cookie. And then at the 144 and 152, we can see the saved RBP. And from 152 to 160, we can see the return address. So let's see if we really can read this data like that. So we will receive 200 bytes as a data. And then because this is a 64-bit machine, I will just split those data into 8 bytes as a chunk. Yeah. Data I 8 plus I multiplied by 8 plus 8 for I in X range when data. So if I do this, it will split by chunk, and then for I, for address in chunks, hex address. So let's check what's in there. My bad. It's SR1, right? SR1. I didn't include the pawn, so from pawn import all. Yeah, then it will work. Then let's run it. And for the address, I cannot change it to the hexadecimal number because I need to apply U64 for making the bytes into integer. Then it will print out some of the data from the leaks. So from the leaked data, we can take a look at some of the values like this. And then can you see stack cookie is somewhere here? So the answer is this part is the stack cookie, this one and this one. So the characteristics of the stack cookie is that the last byte will be 0 to guard some of the ASCII functions. And then the rest of the 7 bytes will be randomized across the execution so that you can see these values as a stack cookie. But let's get it accurate, more accurately. Yeah. So we know that this data will leak the data starting from here. So from the offset 0x88. So buffer is a RBP minus 90, and then the stack cookie is a RBP minus 8. So the distance between the buffer and the stack cookie is a 0x88. So our chunks are like the 8 bytes apart. So if we get that offset divided by 8, so we will have multiple chunks, and then we have a 88, a 0x88 as an offset, and then that's the distance between the buffer and the stack cookie. And then, so if we point that index in the chunk, then we can get these 8 bytes and then print out. So if we print out the hexadecimal number of that one, stack cookie, so this value is the stack cookie that we get. That's actually exactly at this point. So this is the buffer start, and then buffer ends at here. There's a stack cookie, and then saved EVP, and then return address. So let's do a more interesting thing. So we collected these 3 data from here. And then we know that the buffer structure is that we have a buffer and then stack cookie. So the stack cookie is here. And then the saved RBP will be right next. And then return address will be the next one. And then why does this matter? Because like right now, we have the PIE binary. So all the code and data area of the program itself will be randomizing on each execution. So to do that, we also don't know where the main function is and then where the GOT of the other function is. And then we need to identify that first. And to do that, because all the code and data area are relative to one of the fixed base address, and then if we can leak any address in the code, then we can identify, we can break the ASRL for the entire code area. Yeah. And to do that, we can focus on the return address. So I just told that this is a return address, and then the randomizing is done based on the page aligned. So if we can focus on the last 3 digits, then we can verify that's actually the code address or not. Yeah. And then let's focus on 9F6 here, the address that we leaked. So 9F6, and then let's try to find what that address is. Yeah. So go to the SR1 and then disassemble the input function. And because this binary itself is a position independent executable, so it has no fixed address, so it only has the offsets. Yeah. And then what we have seen for the offset was 9F6. Yeah. So right after the stack cookie is here, save the EVP, and then return address 9F6. And then this is an input function, and input function is called by the main function. And then, so the main function calls the input function like here, and then when we call the input function, we will store the next instruction address as the return address. So the main function will store the return address of the 9F6 and then add whatever base address of the code, yeah, here, yeah, as the return address. So then now the program is simple. The offset of this return address is 9F6. Then the address that we got from the stack leak was like something 9F6. Yeah. So what we know is, so this position will store this address because 0x88, 9 divided by 8 will point to here, plus 1 is here, plus 1 is here. Yeah. So this will be the return address. Then subtract 9F6. Then we can get the code address base here. Yeah. And then from this leak, we got the value of the stack cookie. So stack cookie value as here, and then code address space. And then let's check if our stack cookie value is correct or not. And to do that, right after having this kind of leak, we can have the chance to exploit the buffer overflow vulnerability. And then for doing that, I can set up the buffer as a multiplied by 0x80, and then add the stack cookie value. And then save the EVP. We don't care. Yeah. And then add B as a return address. Then it should fault at the 42424242. Yeah, because we put the B as in the return address. Then send the buffer. And let's try to run it. This is something weird. I didn't insert Peter Interactive here, so that's why. So we got the EOF, and then the program got the segmentation fault. And then let's check the core file. And then it says it returns to 4242424242. That means we match the stack cookie. That is, if we change the value of the stack cookie, maybe -1 or something. So if we put a different value, yeah, then it will say stack smashing detected, so it's terminated, sig abort, so we cannot do the exploit. But if we match the stack cookie value from the leak, then we can overflow and run another code. So right now we know how to change EIP. Then where do you want to run? That's the next problem. Yeah. And then now we know the code base address. And then another thing is that, so this is the code offset, the output. And then we need some the string. If we run the system or execv or execv, those kind of function, we need the some string. And then at the address 0x20, yeah, offset 0x20, we have a character at here. So the one thing that we can do is ADDR of the @sign is at the code address base plus 0x20. Yeah, that's the thing. And then what we want to do here is that instead of the running B, so we want to call something like this. And then to do that, what we want to do is buff plus P64 pop RDI return, and then buff plus P64 ADDR at, yeah, 64P RSI R15 return. We usually have 64 0 0, and then libc execve. Then we can call execv at 0. Yeah, so this is good. Yeah. So by doing this, we can run at, but the problem is that how can you get the address of the pop RDI return and pop RSI R15 return? So we can get that from the wrap gadget. Then do wrap gadget SR1, and then we will just get all the offset. And then what we need is these two gadgets, so RDI and RSI, and copy that. Then just get it here. So pop RDI return is at a code base address, because these are all offset, because now we know the code base address, code address base, right? That's the right name. Plus 0xA63 was the pop RDI and return. Pop RSI and R15 return is the code address base plus 0xA61. Yeah. So all these threes are okay, but the problem is that where is libc exactly? Yeah, libc address. So to do that, we at least know where the libc function is, and then to do that, we need to exploit the vulnerability again. Yeah, to leak the libc address. But there is another way doing that by taking a look at the stack and figure out where your buffer is, where the library code is. So one of the interesting thing is that, so suppose you are running the main function. Yeah. So suppose you are running the main function. So from SR1, yeah. And then if you run the start command, it will start at run as start, and then if you're just following the functions, then it will call libc start main. But the last push of the first argument of the libc start main function is the address of the main. So right, so this is the address of the main. But the libc start main internally, it will call the main function. That means main function, it will have the return address, and then address of that will be coming from the libc start main. So let's set the breakpoint at this main address, and then continue. So now we are stopped at the main. But the problem is that, the interesting thing is that so at the start of the main function, so it's a return address. So at the stack, it will, so main function is called by libc start main. So it will point to somewhere in the libc start main. Yeah. So we can get the address of the libc start main somewhere in the middle from there. So this is that address. And then we can also leak that address from the stack. So suppose we can leak that address. Then what we want to do is like the leak that address, subtract the offset of this one, and then add the offset of the execv. Yeah. Then we can run that. So what I will gonna do is I will copy these two addresses. Yeah. And then put it here. And And then what we need to know is like we need to know the address of the libc start main, and also some of the return address of the main, and then calculate the address of the execv, and then use that here. And to do that, we will revisit some of the leaked values from here. Yeah. And then maybe at this time we can length the leak as 400 bytes. So let's try to leak the up to 400 bytes. Yeah. Then it will leak a little more bytes. Yeah. But can you see that this is the exact stack cookie one, and then this is the saved EVP, and then the return address. So 9F6, that's the return address that we have. And then let's take a look at the how main function calls the input function. So this is the main function. And before calling the input function, it will reserve stack as a 0x20. And then there will be RBP, saved RBP, and then return address. So 0x20, which is 4 items, and then saved RBP, and then return address. So we will run this again. So this is the stack cookie, save the EVP, and then return address of the input function. And then the main function will reserve 4 blocks, 0x20 bytes for the stack. So we will exclude these 4 blocks, and then save the RBP, and then return address. So that this address will be the somewhere in the libc start main, the address return address of the main. So that we will calculate the address of the execv from this address. So what we will do is like I will just copy entire thing. So previously we used this table, but right now we will use this table. So at the position 0x88 divided by 8, we have stack cookie. And then plus 1, we have a saved RBP of input function. And then plus 2, return address of input function. And then main reserve block 0, 1, 2, 3. So main reserves the 4 blocks, and then this is a saved RBP of main. And then this is the return address of main, which is libc start main somewhere. Yeah. So index 1, 2, 3, 4, 5, 6, 7, 8. So from the index 8, libc start main somewhere, we can get that address from the 0x88 divided by 8 plus 8, right? 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Then we can get the libc start main somewhere. And then to get the libc exactly the address of this function, then we can get the libc start main somewhere, and then minus 1 instance of that address, and then plus the execve address instance with the same randomization. Then it will subtract the libc start main address and then add the execve address. Then we can finally get the address of the libc execv. Yeah. So this is how we can get the address of the execv. And then let's try to run this. Yeah. Then right now it does nothing. Yeah. Because it will do something, but the problem is that we have the app binary here. So what we can do is code app, and then get EGID for us, and then execve -h 00. And then we will run the exploit script again. Then we can get the group ID by running the add file. So this example is a little sophisticated, but by running the sequential read vulnerability here. So it will leak some of the data in the buffer, but if we didn't fill the buffer, then we can leak some of the data in the stack. And then that contains a stack cookie, saved AVP, return address, and then even stores the return address of the main function, which is somewhere in the libc. So by leaking the stack just for one time, then we can collect all the data required for the code address space and libc address space, and also the stack cookie value. Then finally, we can bypass the security mechanisms. All three security mechanisms applies to this binary with just one sequential read vulnerability. Then we can exploit the buffer overflow vulnerability. So basically, you can regard the sequential read or arbitrary read as some of the techniques to getting more knowledge for the exploitation. So you can bypass these security mechanisms, and you can regard arbitrary write or buffer overflow as an actual action to change the address to divert the control flow from the original one to the something else. So any questions? No questions at all? And the reason why we learn about the arbitrary read and write is like the next vulnerability we will learn, format string vulnerability, which is based on the this kind of the attack. So format string vulnerability will let us do either arbitrary read or arbitrary write, and then we will use the format string vulnerability as the gateway for the having arbitrary read and write, and we will do the similar type of the exploitation by just using printf as our exploitation gate. All right, then feel free to put questions on the Discord, and please have fun with the challenges in week 6, and then that is due on like more than 1 week from now on, so that you will have enough plenty of time. And Thursday is the due date of the week 4 challenges. No, week 5 challenges. So don't forget about the due date, and please submit all the assignments before the due date to take the full credit. All right, thank you for your attention. Yeah, and then let's finish tutorial at here, and then I will post this video to like in an hour apart, because the cloud system requires that kind of the delay. All right, bye bye.